Alright, ladies and gentlemen, welcome to section 4.6, Simpsons and Trapezoidal Rules. Last time, we focused upon using things like U substitution to solve difficult integrals. For today, many of the integrals we're going to talk about are solvable using techniques that we've discussed. However, some are simply not. And to do this, we're going to talk about some of the classic ways we can look at alternatives to the methods we've talked about, specifically numerical integration. Now, let's remind ourselves. From way back about 4 weeks ago, my God, we talked about how if you have a curve and you want to find the area that is underneath it, one of the things we can do is to break it into pieces and do a square counting technique, kind of like what you do almost in like an elementary setting. You'd be like, oh, let me just count the number of squares that fit in here. We talked about how we could do something called the left-hand method, where you look at the left-hand side of each rectangle and use it to turn each of these little curves into little rectangles. It was kind of tedious, if you remember, and led to some interesting scenarios, like this one, where some of the rectangles are clearly too small, some of the rectangles are clearly too big. We talked about an alternative to that one, which was like the right-hand rule, which did the opposite effect. So instead of looking at the left-hand values, it looks at the right-hand values of each of these little pieces and attempts to determine the size of the rectangles using the left-hand value instead. And so it's just an alternative. So in this case, both are going to be off by a certain amount, but both have gotten closer the more and more we get to infinity. Remember, the number of rectangles we have is considered to be the value of n. And so in this example, 1, 2, 3, 4, 5, 6, 7, 8 rectangles would mean we have an n of 8. We also talked about delta x as representing how wide each of these rectangles was. But before we went on break, one of the things we talked about was that we're choosing to turn these into rectangles. We have a choice of that. And for some problems, we chose other shapes, like we turned them into triangles, or we turned them into like half circles or full circles and stuff. But there are other options, and that's where these two rules today come into effect. These two rules that we're going to talk about today are both faster than doing either the left-hand rule or the right-hand rule. And they are more accurate for the same value of n. So for today, the big notes. We're still doing a narrative approach, so we're looking at the numerical part of this. However, the big difference is this, in theory, should be faster and more accurate for the same n. That's the big deal. So we're going to come across some problems today that are simply not solvable no matter which technique you want to use. And when that happens, these techniques, like we could go back and use the left-hand rule or the right-hand rule from section like 4.2, but they are just not great methods, because if we want to get an accuracy of a specific amount, like let's say we're designing an airplane foil, and you want to have an accuracy of something like 0.001, so a thousandth of an inch. That's actually reasonable for mini designs, although you're more likely to get into the hundredth of an inch category. If you want to do that with the left hand and right hand rules, you might have to go to n equals 60, which is big. If you're doing it by hand especially, that's a pain. You now have 60 rectangles to look at. You got to find the deltas for those 60 rectangles and the f of x values, the heights for each of those rectangles, and then add them all together. That can be a pain. For the trapezoidal rule, the first one we're going to talk about, you might need an n of like 12 by comparison. And for Simpson's rule, which is even more accurate, you might need an n of like 8. And so you can see quickly that these two are going to be significantly faster and more accurate. And even if you're using a computer program, like a computer can pump out these 60 calculations in half a second, but it can pump out these 8 calculations in a hundredth of a second. You know, it's a big difference, even if you're using something like a computer or a calculator. We spent some time doing some of these problems on the calculator, and doing it on the calculator would take a long time. Like, we'd sit there for 2 or 3 or 4 minutes sometimes waiting just for the calculator to pop out the answer. If the calculator was using a better rule, it'd pop out the answer faster. And there are ways you can actually get it to do that. Well, you can use Excel to do a lot of mathematics like this for you. But if you're going to do it, you'd much rather do it with this rule, which has a much lower value of n, than with this rule, despite them both being the same process, converting this shape into a bunch of smaller shapes, and then adding them all together. So, anyways, again, the big draw of today is going to be that each of these components that we're going to talk about, each of these little pieces, are going to have all these little parts to them that are going to be faster and easier to use if we have these extra techniques. If we don't have these extra techniques, they're either impossible or they're significantly slower. So let's take a look today. We're going to look through a couple of examples of both the trapezoidal and Simpson's rules. For both of them, the trickiest thing about them is they have equations associated with them. And these equations are interesting. You need to pay close attention to what they look like and how they fit together. So let's pull out a fresh sheet of paper and look at the first rule we're going to talk about, which is the trapezoidal rule. So, trapezoidal rule. As the name implies, the trapezoidal rule is going to say, okay, you have a shape. Instead of breaking them into rectangles or any other kind of shape, what this rule is going to do is going to attempt to break these apart into trapezoids. So it's going to make one trapezoid, or possibly a triangle here, one trapezoid here, one trapezoid here, and one trapezoid here, and one trapezoid there. Even just eyeballing this, if you were to compare this to something like the left-hand rule and right-hand rule, it's going to be significantly more accurate, right? The right-hand rule is going to be way too big for some of these, and way too small for other ones. Right? Look at how much closer these red lines are compared to these darker lines. Like, it's going to be so much more accurate doing it with these red lines, making little trapezoids as opposed to making little rectangles. And it's the advantage of having this rule that lets us do that. And same with the right-hand rule. It is so much faster and faster. Easier is going to be a relative term here. It's so much faster and simpler to do with these little red lines than it is with these larger lines that are outlining them. And it's going to get us the answer significantly faster, especially if we're playing with something real world that needs very precise solutions. So in the text, they offer some great explanations of like where to get the rule from. But for the big one, I'm going to focus on the theorem. If you want to see where this formula comes from, you can read through this particular section, and I'll attempt to explain where it is the formula came from, which is nice, but not necessary for us. Let's take a look at theorem 4.17. Called the trapezoidal rule. So, this theorem, like with many of the theorems in this section, has a few caveats. First, it has to be a continuous function. This can only work if the function is continuous. There can't be any holes. There can't be any asymptotes. It has to be a continuous function in order for this to work. So, we have to have continuous on the specific interval from a to b. Okay? Now, what it states is, if you have the integral from a to b of the function f of x dx, it is going to be roughly equivalent to this formula. B minus a over 2n times f x sub 0 plus 2 f of x sub 1 plus 2 f of x sub 1, 2 plus continuing until you get to the last two, 2 f of x n minus 1 plus f of x sub n. The pattern here is the first and last are just f of x's. Everything else is 2 f of x. for any value you have in terms. So, and as the number n approaches infinity, as you can see right here, these two become equal. So they're close. This little approximation symbol indicates they are close in value. But as n becomes infinity, they become the same. So there's an example in the book that we're going to use, which I will come back to. I will do that one second, actually. But I'm actually going to use a different one to get the same basic results. And in this case, the one I'm going to use is going to be a simple equation, f of x squared. It's actually very similar to your first problem, so this will be a good one to look at. Okay. Trapezoidal rule. Example 1. So, in order to use the trapezoidal rule, you need to have two components, right? We need to know what the function is, as well as its boundaries. We're going to go, for this case, from 0 to, let's say, 4. Okay? Second thing we need is we need to know n. So I'm actually going to do this twice. Once, where n equals 4. And then again, where n equals 8. Now, based upon the information given, we could easily integrate this using another technique, and I will at the end, to verify just how accurate our answer is. Because, as it turns out, for each one of these, this gets you a more accurate answer for fewer steps compared to the other numerical methods. So again, compared to the left-hand rule and compared to the right-hand rule, this will give us a more accurate answer faster. But in order to make that work, we got to first show that the numerical methods are going to work too. So I'm going to draw my little picture. We're going from 0 to 4, so I'm just going to focus on the 0 to 4 part of this. So in this case, we just go to 1, then we go up to 4, and then we quickly go off the page. So we're going from 0 to 4. And our first step is going to be, we're going to break this into 4 rectangles. So if we're looking at this, if we're going from 0 to 4, well, that makes it really simple. We're going to break this down into, what the heck? Sometimes I miss you guys just because you guys would help point out some stupid things I do sometimes. So we're going from 0 to 4, and so you can see that if we're doing it from 0 to 4, and we're doing n equals 4, that just means we're going to break it up into these trapezoids. So again, this will be our first trapezoid, this will be our second trapezoid, that'll eventually be our third, and our fourth will be up there. So when n is 4, we're just counting by ones. So let's talk about the formula. The formula is the integral from 0 to 4 of x squared dx. Now, we're doing this into 4 pieces, so we're going to do, okay, my formula, let's put this up here so I don't lose it. Alright, there it is. Cool. Alright, so we're going to do b minus a, so that'll be 4 minus 0 divided by 2 times n, and in this case is 4. Okay, parentheses. F of x sub 0. F of x sub 0 means f of the first value. So f of the first value, this will be f of 0 plus 2 f of the second value. Well, my second part of the box is at 1 plus 2 times f of 2 plus 2 times f of 3 plus 2 times f of 4. 4 is our last value, so that means it's not 2 times, it's just f of. Remember, the first term and the last term are just singulars, everything else is 2. Notice that the number of terms inside is n plus 1, so we're breaking it into 4 pieces. We'll have 5 terms, 1, 2, 3, 4, 5. This is because, remember, you're talking about the endpoints. So this one and this one has 2 endpoints. Add one more endpoint, one more endpoint, one more endpoint for a total of 5 endpoints for each one of these. Now, to evaluate this, this is when n equals 4. Let's actually do this. 4 minus 0 is 4. 2 times 4 is 8. We'll simplify that in a second. Okay, f of 0. Well, I plug 0 into my original function. My original function is f of x equals x squared. Plug in 0, 0 squared, plus 2 times 1 squared plus 2 times 2 squared plus 2 times 3 squared plus 4 squared. Remember, your last term is just a singular. All the other ones are doubled. Okay, equals 4 over 8 becomes 1 over 2. 0 squared is 0. 1 squared is 1 times 2 is 2. 2 squared is 4 times 2 is 8. 3 squared is 9 times 2 is 18. 4 squared is 16. Okay, 1/2. 2 and 8 is 10, plus 18, that's 28, plus 16, that'd be 44. So half of 44, which is 22. That's pretty good. All right, let's do the same process now. As with many of the problems you'll have tonight, you may have more than one problem you need to do. So let's do the exact same process, but now doing it for n equals 8. So if n is 8, that changes our setup just a little bit. But the same basic rules are going to apply. We're still doing an integral from 0 to 4 of x squared dx. But now if we're doing it from 0 to 8, it's going to change how I do my picture up here. Instead of doing each of those trapezoids, we're going to cut each of these trapezoids in half again to get a total of 8 of them. Okay? So this means we're going to have, 4 minus 0, so b minus a over 2 times n, and in this case being 8. Okay. All right, we got to do, our first dot is at 0. Our next dot is going to be at 1/2, because we're breaking it into 8 little mini, not rectangles, but trapezoids. So 2 times 1/2 plus 2 times 1 plus 2 times 3/2. I'll drop my f's. Plus 2 f of 2 plus 2 f of 5/2 plus 2 f of 3. I'm running out of paper here. Plus 2 f of 7/2 plus f of 4. Okay, not exactly a short problem, but relatively simple. And so we've taken our function, our integral, we've plugged in b minus a over 2 times n, and then on here we have our first coordinate, 0, our 2 times the f of our second coordinate, so 2 times 1/2, plus 2 times f of our third coordinate, which is 1, 2 times f of our fourth coordinate, which is 3/2, and then continuing on until we run out of coordinates. Now, let's simplify. So, our answer for our previous problem, its relatively low accuracy, is 22. Let's now do this one. 4 minus 0 is 4. 2 times 8 is 16. All right, let's plug in. F of 0 is still 0. 2 times 1/2 squared. 2 times 1 squared. 2 times 3/2 squared. 2 times 2 squared. 2 times 5/2 squared. 2 times 3. 2 times 7/2 squared. And then 4 squared. All right, let's simplify. 4 divided by 16 is 1/4. So notice how the first number has changed because we have a different n, but what's inside has also changed, so it's going to roughly get very similar results. 0 squared is 0. 1/2 squared is 1/4, and 2 times a fourth is actually 1/2. So I'm simplifying some as I go. 1 squared is 1 times 2 is 2. Let's see. I think every other one of these is going to be nice. 2 squared is 4 times 2 is 8. 3 squared is 9 times 2 is 18. And then 4 squared is 16. Let's do the nasty ones now. 3/2 squared is going to be 9/4 times 2. That's going to be 9/2. 5/2 squared is 25 over 4 times 2 is 25 over 2. And then 7/2 squared is going to be 49/4 times 2 is 49/2. All right, let's put them together. 1/4 times, okay. 0 plus a half is 1/2 plus, okay, I'm going to do the easy ones first. So these three are going to be 22, because it's the same problem we had up there, plus, okay, 1/2 plus 9/2, that's 10 halves, plus 25, so that'd be 35 halves, plus 49, that'd be 84 halves. 84 halves is equivalent to 42. 42 and 22 put together is 64. And 1/4 of 64 is 16. Okay. So these two numbers not as close, but what I want to point out here is what the actual answer is. So let's integrate real quick between 0 and 4 of x squared dx. So if I integrate this, I use my standard power rules, this would become 1/3 x cubed from 0 to 4. 0 is not going to do anything, so we do 1/3 of 4 cubed. 4 cubed is 64 divided by 64 over 3. And 64 over 3 is 21.3. These two will keep yo-yoing back and forth until eventually they become roughly the same value. And it's always possible I made a mistake somewhere in here. Let me double check. 0, 2, 8, 18, 16. That should be 22. I'm dumb. I'm so sorry. This should have been a 44. Okay. 44 plus 42. I'm glad I checked my results, right? You should too. 44 plus 42, that's 86. And 86 of 1/4 of 86 should be 21.5. Look how close that is with only n equals 8. Like, we couldn't get this close for n equals 8. We couldn't get that close with the left-hand rule or right-hand rule unless we got like 20 or 30. Like, it's impressive how quickly, even with n is 4, look how close that is. Right, that is so much closer. If you did the left-hand rule, I believe you get a value of like 12. And if you do the right-hand rule, you get a value of like 40. Like, they're really far apart. Whereas this one, just with n equals 4, you're really close. I mean, you are so close with n equals 4. And then with n equals 8, like, you're even closer still. You're almost within 1 decimal place for only doing this out to 8, and that didn't take much time at all. So this is the trapezoidal rule, and we'll do the second one, the one they do in the book, afterwards. But this is the process. You take this integral, and you use the formula to plug in all these little values, and then it pops out a solution. The nice thing about the trapezoidal and Simpson rule is it's pre-written. Unlike the left-hand and right-hand rule where you have to kind of figure out what all the numbers are supposed to be, they're already here. They're already waiting for you. You just got to plug and chug. That's the nice thing about the trapezoidal and eventually the Simpsons rule too. So there you have it. Let's do example number 2 with the trapezoidal rule. And this will be the one out of the textbook. And again, it'll be using 2 different values of n, where we have n equals 4 and n equals 8. And you can follow along in the text if you wish, there on page 312. Okay, boom. There's my rule up there. This is the example from the text. This is example 2 from the textbook. And the integral they're doing is between 0 and pi of sine x dx. Unlike last time, this time I'm going to go ahead and find my solution. My solution for this problem, if I do it by a standard technique, so from 0 to pi of sine x dx, the integral of sine is negative cosine between of x 0 and pi. So that's your standard conversion. The integral of cosine is, of sine is negative cosine. And then we plug in. If we plug in pi, so you have negative cosine of pi. minus cosine of 1. And let's see, cosine of 0. Let's see, this should become negative 1. And at negative 1, we should get a value of 2. Although negative 1 make this positive. Negative cosine of pi would become negative negative 1, which becomes 1. Plus cosine of 0 is 1, which gives us the value of 2. There we go. And so we should get a value of close to 2. And you can see here in a moment, if you look in the text and see ahead, that it does very quickly. So let's look at 4 and 8. So first example, let's do n equals 4. So we do the integral from 0 to pi of sine of x dx. All right, we do b minus a, so pi minus 0 over 2 times 4. So b minus a over 2n. Okay, now, if I look at my integral that we're doing here, helps to have a picture, between 0 and pi, here's my sine function. We're breaking this into 4 groups, so halfway through should be pi over 2. Next group should be pi over 4 and 3 pi over 4. There we go. And so there's my 4 little pieces. And now let's actually, plug in our values. So our first is going to be f of 0 plus 2 f of pi over 4 plus 2 f of pi over 2 plus 2 f of 3 pi over 2 plus f of pi. There we go. Let's solve. Pi minus 0 is pi. 2 times 4 is 8. Okay, f of 0. Sine of 0 is 0. Pi of 4 is square root 2 over 2 times 2 plus sine of pi over 2 is 1, so that'd be 2 times 1 plus 2 times sine of 3 pi over 2 is square root 2 over 2 again, plus sine of pi, which is 0. Okay, so we have pi over 8 times, okay, zeros are going to go away. 2's and square root of 2's, these are going to cancel on bottoms. So we end up with 2 square root 2 plus 2. It's a little strange, but okay. And if we plug this into a calculator, we get an answer of 1.896. Which you'll notice, that's pretty darn close. Like our predicted answer was 1.896. That's within, 0.11, 11 hundredths. That's pretty dang close. If you were measuring something by hand, this would be appropriate. Like within 11 hundredths, that's better accuracy than I would get with a ruler. So there you go. But now let's do the same thing with n equals 8. Okay, integral from 0 to 4 of sine of x, from 0 to pi, getting to left of that mindset, of sine x dx. Okay, if we're doing it with 8, we got to break each of these rectangles apart again. Okay, 8 rectangles is going to make this pi over 8. It's going to make this 3 pi over 8, 5 pi over 8, and 7 pi over 8. All right, let's do this. So it becomes b minus a over 2 times n. Okay. Now I gotta plug in all these values. All right. So we plug in. We would do f of 0 plus 2 f of pi over 8 plus 2 f of pi over 4 plus 2 f of 3 pi over 8 plus 2 f of pi over 2 plus 2 f of 5 pi over 8 plus 2 f of 3 pi over 4 plus 2 f of 7 pi over 8 plus f of pi. Now, calculator's assistant here, I'm not going to do all this by hand because some of these are not in my unit circle. Like pi over 8 isn't in the unit circle, neither is 3 pi over 8, any of the pi over 8s are not in there. So I would go ahead and bust out a calculator here, and when you do, you get an answer of 1.974, which you'll notice, if my known or supposed value with my standard integration is 2, and I have 1.974, you're within 0.03 of the right answer. Like, this is my error, as we call it. Like 300ths is nothing. You would not get that close of an accuracy with any ruler that you have. It's impossible. And so going just out to 8, just 8, got us 300ths of an accuracy. That is almost what you would expect in a car manufacturing system. Like if you were manufacturing car parts, most car parts have a tolerance of 1/100th. So maybe if you went out to 9, you'd have 1/100th, or 10 maybe even. And that's impressive for only going out to 8 rectangles. Like, if we were doing this with the left-hand and right-hand rules, you'd expect to be still off by almost half an inch here, or half an area unit. And so this is amazing what the trapezoidal rule can do, is get you this accurate of an answer with only 8 rectangles. And so this is the trapezoidal rule. Notice it is entirely formula driven. You have to use the formula, and you have to know the formula to use the formula. If you wish to do well on your AP exam, memorizing this formula and the Simpsons formula is one of those steps. You've got to do it. So we are officially about a third of the way done. Let's now look at the same process using our second rule. Our second rule is referred to as Simpson's rule. Now, Simpson's rule. This is not related to Homer Simpson, although there is a fun theorem related to the Simpsons that if you ever care to look it up, it's pretty funny. The Simpson's rule is referring to the fact that, well, we have so far, we have tried rectangles. In fact, we've tried many different kinds of rectangles. And now we've tried trapezoids. Like, both these are still elementary shapes, and you can do other rules that are related to elementary shapes, but the Simpsons rule attempts to go farther, where instead of doing it with a standard shape, you do it with a curve. In this case, a parabola. There is a farther rule, I cannot remember its name at this time, where they do even more advanced curves, because a parabola is considered a basic curve. It's the first degree up from a line. But you can do it with a cubic curve or with a quartic curve and be even more accurate. There's no nice way to write them. Simpson's rule has a relatively nice way to write them, just like how the trapezoidal rule has a relatively nice way of writing it. It's not the nicest to write out, but it is easy to remember. First and last are the same, and all the other ones are doubled. Straightforward. Okay, Simpson's rule. There's a lot of text in the book showcasing where the Simpsons rule comes from, and I think it's useful. It showcases here how we have the integral and turning all the integrals into these polynomials, and then rewriting the polynomials into a form which can then be rewritten into Simpson's rule. I'm going to jump straight to Simpson's rule. If you want to know where Simpson's rule came from, please take a look at the section. So, Simpson's rule. The point of Simpson's rule is we're not going to be using lines or rectangles or trapezoids to find it. We are using curves. Because we are using curves, it has a more complex formula, but because we are using a more complex formula, it will get a faster, more accurate answer. And for this next one, when we do Simpson's rule, we will redo the previous two problems. So the example 1 we did, we're going to redo it with, again, n equals 4 and n equals 8, because we know what those answers should be. This will give us an easy frame of reference to see that Simpson's rule is better. All right, just like before, in order to use this rule, you can see here, f needs to be continuous, and n needs to be an even number. So f needs to be continuous from a to b, And this is the other part. N needs to be even. This does not work if n is odd. It does not work. And so it limits what you can choose as your n, but that's okay. Okay, so what's it state? The integral from a to b of f of x dx is roughly equivalent to b minus a over 3n times f of x sub 0. This is our first x value, plus 4f of x sub 1, plus 2f of x sub 2, plus 4f of x sub 3, plus dot dot dot, so continuing, 4f of x n minus 1 plus fx sub n. So you can see it follows a slightly more complex rule. In this case, the pattern is first and last are just f of x's. Then it alternates 4, 2, 4, 2, so on and so forth. It will always start on a 4 and end on a 4. And so you can see up above an example of when you have only 3. It would be just f of x plus 4 plus f of x. So the first and last are always by themselves, and then it starts at 4 and then alternates ending at 4. So yeah, and you can see down here a different example of this right here, written as the following pattern: 1, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, 1. It'll always start on a 1 and end on a 1. The next one will always be a 4. The next number will always be a 2, and so on and so forth. Okay, just like before, we're going to do these exact same examples as we did before, but this time using Simpson's rule. And the nice thing is we're going to reuse some of our work. So let me pull up our previous work here. Okay. So with the trapezoidal rule, we got an answer of 22 with n equals 4. And remember, our supposed answer was supposed to be 21.3, so we were pretty dang close. But now we're going to try it with Simpson's rule and see when we have an n of 4, just how close we get. Okay, so I'm going to bring this up. Let's go ahead. Okay, so same problem. So we're doing n equals 4 for the integral between 0 and 4 of x squared dx. Okay, so just like before, we're going to use our same basic picture, what we had up here. So in this case, we're just doing 4 rectangles. So we're going to do 0, 1, 2, 3, and 4 as our boundaries. And now, let's take a look, shall we? This is going to be roughly approximately equal to, so we do b minus a over 3n. So 4 minus 0 over 3 times, if we have n, that would be 4. Okay. Then we do f of the first value, so that would be f of 0 plus 4 f of 1 plus 2 f of 2 plus 4 f of 3 plus our last one, which is f of 4. Notice it starts and ends the same, and then it goes 4, 2, 4, and then continues that pattern until it runs out. All right, what's this equal to? Well, 4 minus 0 is 4. 3 times 4 is 12. F of 0 is 0 again, plus 4 times f of 1, which would be 1 squared, plus 2 f of 2, so f of 2 would be 2 squared, plus 4 f of 3, which would be 3 squared, plus 4 squared. Apologize for my bad handwriting today. And always. 4 over 12 is 1/3. F of 0 is 0. 4 times 1 squared. 1 squared is 1 times 4 is 4. Plus 2 squared is 4 times 2 is 8. plus 3 squared is 9 times 4. 9 times 4 is 36. Plus 4 squared is 16. Alright, 1/3 times 0 and 4 would make 4, plus 8 is 12, plus 36 would be 48, plus 16 would be 64. And 1/3 of 64, that is 21.3 repeating. Hey, look at that. With only n equals 4, we got an exact right answer. That's pretty impressive. Like, 4. It works. Now, the consequence of that is because we're dealing with x squared, so it should fit nicely, because remember, the Simpsons rule is based upon a parabola. Using a parabola to get a result rather than a trapezoid or a rectangle. And so, parabola gets a good result for a parabola. Who knew? It turns out 8 will get you the same exact answer, because that's how the trapezoidal rule works. And so now, I'm going to jump straight into example 2. So for the example 2, we had the integral from 0 to pi of sine of x dx. And for that example, remember, our expected answer was a value of 2. And we got close with n equals 8 of 1.974. That was pretty dang close. But now let's see how close we can get now using Simpson's rule. Okay, so same basic setup, but instead this time we're going to be using Simpson's rule instead of the other rule. So let's set it up and let's start solving. Okay, so alright, we are now using Simpson's rule, so we do integral of b a, there we go, okay, so we do b minus a, so that would be pi minus 0 over 3 times 4, so b minus a over 3n, parentheses, we would do f of 0 plus 4 f of pi over 4 plus 2 f of pi over 2 plus 4 f of 3 pi over 4 plus f of pi. Okay, what's this equal to? Okay, we should expect to get an answer that is near 2. So let's find out. Pi minus 0 is pi. 3 times 4 is 12. Okay. F of 0 is 0, because sine of 0 is 0. Plus 4 times f of pi over 4. Sine of pi over 4 is square root 2 over 2. Plus 2 times f of pi over 2. Sine of pi over 2 is 1. Plus f of 3 pi over 2. 4 times f of 3 pi over 2 is square root 2 over 2 again. Plus f of pi, which is 0. Okay, so we have pi over 12 times, okay, the zeros cancel. 2 times 1 is 2, and the 4 and the 2 are going to cancel, meaning we end up with, okay, so 4 and 2 cancel, leaving a 2. 4 and 2 cancel, leaving a 2. 2 and 1 leaves a 2, okay. So we end up with 4 square root of 2 plus 2, which is equivalent to, let's see, I think they actually showed my work for me, which is super helpful here. Yep. Look at this. Look at that. That is just amazing. Like, just compare. Like, to get even close to that, we had to go out to 8. When we went out to 8 before, with a previous example, we had to go, and we still had an occ of about 0.03. Now we're within 0.005. We're at a full factor of 10 closer. This right here will be close enough to build an airplane with and have good tolerance. Like, with 8, we couldn't even get the tolerance needed to build a car, which is much less tolerant than a plane. And so, with just going to 4, we were able to get that close. And as you can see in the text, they go out to 8 in a similar process, and it's even closer still. And so, by comparison, these will always be significantly faster in terms of n. Like, faster in this case just means fewer n's. And yeah, they're more complicated than the left-hand right-hand rule, because the left-hand rule, you just have to look at it and go, okay, pick the left-hand values. The right-hand rule is, oh, okay, look at the right-hand values. But these ones, they have to use a formula. And if you're not a fan of formulas, then you're not going to be a fan of these problems. So I'm sorry to say, get over it. It's just the way it works. All right, last piece, error analysis. Okay. The Simpsons and trapezoidal rules both have ways to approximate the error, meaning you can predict before you start how far off your answer is going to be, which is kind of impressive. This is theorem theorem 420. Very appropriate. Theorem 420 is errors in trapezoid and Simpson. So, if you're looking at the trapezoidal rule, let's write them out before we begin. The trapezoidal rule has the following error. The error, how far off we are, is equal to this formula. These are again found in your text. Okay, let's explain some of these pieces, because this looks like gibberish until you get used to it. Okay, this means it's the error. Notice that it's an absolute value because error is always positive. So if we're below, our error is a positive error, just it's below it. And if we're above, it's a positive error above it. Error is always assumed to be positive. It's just the way it works. These two pieces are all easy to explain. B and A are the two boundaries, of course. N is the number of units we're using. And you'll notice as n goes to infinity, it doesn't matter how big B and A are, because it is n, it is going to drop this term to 0, which means the entire thing becomes 0, meaning the error becomes 0, which is why these two are equivalent. Now what this says is, we need the maximum value between A and B of the second derivative. Okay, so your error is going to be plugging into this formula. Notice that in order to find the error, you need to be able to take a second derivative, which it says in the error instructions right here. If f is continuous, or if it has a continuous second derivative on the interval, then you may approximate the error using the formula. So that's the trapezoidal rule. Now let's look at Simpson's rule. Okay, again, the absolute value of the error is less than or equal to b minus a to the 5th power over 180 n to the 4th times the max of f4 of x when a less than or equal to x less than or equal to b. Okay, just like before, we have the error. We have here, it's the max value between a and b of the 4th derivative this time. Okay. Okay, so you can use this in two different ways. You can approximate the error, or you can find n that will get you the error that you want. So for example, if I have this example, and again, we can use the one in the text, but I'm going to choose to ignore the one in the text for now. I'm going to come back to it. I think the one in the text is a little easier. So example, let's say we have the integral from 1 to 3 of let's say x squared plus sine of x dx. You might ask the question, okay, what's the error going to be if I'm using the Simpsons rule or if I'm using the trapezoidal rule? So in this case, we're going to let both these, and we're going to use the same n. Let's do n is 6. We're going to find the error of each one of these, which there are a few homework problems that ask you to do this. So let's do it, starting with the trapezoidal rule. Okay, so to use the trapezoidal rule, I'm going to plug in to this function. So to find the trapezoidal error, so the error is less than or equal to, okay, we do b minus a, so that'd be 3 minus 1, that's the third power, divided by 12 times our n, which is 6 squared, times, this is the fun part, the max of x squared plus sine x, second derivative. Okay, now this part I'm going to do separately. I'm going to do it up here in this corner. So the first derivative would be 2x plus cosine. So remember, the derivative of x squared is 2x, derivative of sine is cosine. And the second derivative, okay, that would be 2, because remember the derivative of 2x is just 2, and the derivative of cosine is negative sine. Now, you can find the maximum using a graphing calculator or any other tool you wish. That's what I'm going to do. I'm going to use my graphing calculator real quick. Okay, use your graphing calculator, trying to approximate the maximum. Okay, this appears to have a maximum value of 3. Notice it does not matter where this max is. It matters what the max is. And so for this case, I have my function, and as it turns out, it'll happen at pi over 2, which is within the boundaries of these two numbers. Okay, now I can plug in. So the absolute value of e is less than or equal to 3 minus 1 is 2. 2 to the third power, I'll do in a second. Let's see, 6 squared is 36. I'm going to do 12 times 36 next. And the max of those is 3. So the error is, let's see, 2 to the third power is 8 times 3 over 12 times 36. I'm going to use some quick mental math here. 3 and 12 are going to cancel, leaving 4 behind. 8 and 4 are going to cancel, leaving 2 on top. 2 and 36 are going to cancel, leaving 18 on bottom. So that'll be 1 over 18 as our error. Ooh, that wasn't too bad. Notice that this maximum is a number. It is the maximum in between the two values, always. It's the max that exists for this function in between these two values. And if the max is a 3, I don't care where it's 3, as long as it's within these two boundaries, and it is. So there's what happens when n equals 6 for the trapezoidal rule. So 1 over 18. 1 over 18 is 0.005. So you're within, 500ths, or give or take a little bit. That's pretty dang good. But let's compare that now to the Simpsons rule. So we use the absolute value of e is less than or equal to. All right, for Simpsons rule, different formula. So I go to the second formula. I would do b minus a, so that would be 3 minus 1 to the 5th power this time, divided by 180 times 6 to the 4th, times the max of the 4th derivative of the function. Okay, I already have 2 derivatives because of the Simpson's rule, or sorry, from the trapezoidal rule, so I'm just going to keep going. So the next derivative would become, derivative of sine becomes cosine, but it's negative, so negative cosine. And then the derivative of negative cosine would become positive sine. Remember, cosine becomes negative sine, but it's already negative, so it would make it positive. And the max of sine of x is 1. That happens also at pi over 2, so I know it works. Okay, well, let's plug them in. E less than or equal to. All right, 3 minus 1 is 2 to the 5th power. 180 times 6 to the 4th power is 1296. The max of these ones is 1, so that's pretty nice. Okay, so that means the absolute value of E, okay, 2 to the 5th power, 32. Oh my gosh. I can't do that in my head. Not even close. Okay. Let's start with the simple one. Calculator time. Don't fail me now. 180 times 1296 is, ooh, big number, 233,280, and then 32 divided by that number. That's not right. Stupid calculator. Okay. 0.000137. Like, that's 1/10,000th off. Like, that's, you're talking trajectories on angles in space in order to get it to hit another planet. That's how close you have to be for this. Like, this is impressive. And it's only a 6. Like, look at how fast Simpson's rule got an incredibly accurate answer. Just with 6. It's amazing. And so that's really neat. And there's another example in the textbook to showcase kind of how that also works. You can also use this backwards. All you have to do is plug in the air first and solve for n, which just is algebra. And there's an example of that here, which is really neat. I would recommend you take a look at that in order to determine exactly what the right answer is. And so you can showcase different ways to use Simpson's and trapezoidal rule to get a more accurate answer. And these accurate answers have known accuracies that we can predict using formulas, which is really neat. As a reminder, as we're finishing up today, this is the last section in this chapter. We are coming to a close here. Here we go. As I finish up, homework tonight, pretty short homework assignment. That is because these problems are not short problems, so didn't give you a whole lot of them. 1 through 33, every other odd, and skip number 21. Not too many problems, most of which have you doing both. So make sure you read your things carefully. Notice it says use the trapezoidal and Simpson's rule to approximate the value. So you're going to do problem number 1 once for the trapezoidal rule, and then again doing it with Simpson's rule for whatever n they give you. Make sure to round your answer. And then if you can, find the exact value using a definite integral, which all of these should be able to be done using relatively simple techniques. Hardest one on here is probably going to be number 33, asking you to use theorem 420 backwards. The example is in the text right above it. Please use that to help you. I'm just under an hour. I hope I didn't bore you too much. Last section, we'll have a review passed out tomorrow, and the test either coming over the weekend or on Monday. Let me know what you guys need. If you have any questions or anything, I will post solutions tomorrow, and I will talk to you guys then. Have a good rest of the night. Okay.